Good evening. Tonight, you'll discover how galaxies dance through space, why some stars live for trillions of years, and how the atoms in your body were forged in dying stars. 100 facts about the universe that will guide you into the most peaceful sleep. But first, if you want more journeys like this, subscribe to the channel and leave a like right now, because in just a few minutes, you'll be too relaxed to move. Now then, make yourself comfortable. Let your body sink into your bed. Close your eyes. Tonight, I invite you on a journey through the cosmos, through galaxies spinning in the darkness, through clouds of stardust where new suns are born. 100 remarkable facts, told slowly, gently, without haste. You don't need to remember them. You don't need to analyze them. Just listen. And let these words become part of your dreams. Breathe evenly, deeply. And we begin. Our universe is 13.8 billion years old. 13.8 billion years, not millions, billions. Try to imagine counting to 1 billion, one number per second. It would take you 31 years. Now multiply that by 13. For all that time, stars have been shining, galaxies have been turning, light has been traveling through the void, and here we are, at this moment, looking back across all that time, witnessing the story of everything. The observable universe stretches 93 billion light years across. A light year is the distance light travels in 1 year, and light moves fast, extraordinarily fast, 186,000 miles per second. In 1 year, that's nearly 6 trillion miles. Now multiply that by 93 billion. The number becomes meaningless, too large to hold in your mind. And perhaps that's all right. Perhaps there's peace in knowing some things are simply too vast to comprehend. There are more stars in the universe than grains of sand on all the beaches of Earth. Every beach you've ever walked on, every shore, every coastline, all that sand combined, and still more stars, between 200 billion trillion and a septillion. That's a 1 with 24 zeros, each one a sun, a nuclear furnace, burning quietly in the dark, each one possibly with planets, with worlds, with stories we'll never know. Our galaxy, the Milky Way, is just one galaxy among 2 trillion others, 2 trillion islands of stars floating in the darkness, each one containing billions of suns. Some are spirals, graceful and turning. Others are elliptical, smooth and ancient. Some have no shape at all, irregular clouds scattered by gravity. 2 trillion galaxies, and we live in just one of them. The Milky Way contains between 100 and 400 billion stars. Our sun is just one small light in that vast congregation, one candle in a room filled with hundreds of billions of others. And yet, it's our candle, the one that warms our world, the one that makes life possible on this pale blue dot. If you're still listening, that's perfectly fine. Just breathe and drift. The Milky Way is shaped like a spiral, a great cosmic pinwheel with arms curving outward from the center. It takes 225 to 250 million years for our galaxy to complete one full rotation. The last time our solar system was here, in this exact position, dinosaurs were just beginning to appear on Earth. We're always moving, always turning, traveling through space in peaceful silence. Our solar system sits about 26,000 light years from the center of the galaxy, in a quiet region called the Orion Arm. Not in the main spiral arms, but in a smaller branch between them, a peaceful suburb of the galaxy, away from the crowded center where stars are packed so densely the night sky would blaze with light. Out here, we have room to breathe, room to exist, room to dream. The Milky Way is moving through space at roughly 1.3 million miles per hour, and yet everything seems still. The stars appear fixed, unchanging night after night. This is because the distances are so vast. Even at such tremendous speeds, it takes thousands of years for any change to become visible. Sometimes, the most dramatic motions unfold in perfect silence. Our solar system takes 230 million years to orbit around the galactic center. Since the Sun formed about 4.6 billion years ago, we've completed roughly 20 trips around the galaxy, 20 journeys, 20 great circles, and we're still here, still turning, still traveling. The nearest major galaxy to ours is Andromeda. It sits 2.5 million light-years away, our closest neighbor among the large galaxies. On dark nights, if you know where to look, you can see it with the naked eye, a faint smudge in the constellation Andromeda. But that tiny smudge is an entire galaxy, 1 trillion stars shining across the void. Andromeda contains approximately 1 trillion stars, more than twice as many as our Milky Way, a galaxy richer in light than our own. It spans about 220,000 light-years across. If you could see it in full detail, it would appear 6 times wider than the full moon in our night sky. But it's faint, distant, just a whisper of light traveling across the darkness. Andromeda and the Milky Way are moving toward each other, not away, as most galaxies are, toward. In about 4.5 billion years, they will collide, or rather, they will merge. It will be slow, graceful, a cosmic dance lasting millions of years. But don't worry, by then, the Sun will already be nearing the end of its life. And when galaxies merge, stars rarely collide. Space is too vast, too empty. When galaxies merge, something beautiful happens. Despite billions of stars, actual collisions are extraordinarily rare. Stars pass by each other, like ships in an infinite ocean, never touching. The distances between them are simply too large. It's a collision. That isn't really a collision at all. Scientists have named the future galaxy from this merger. They call it Milkomeda, a blending of 2 names, 2 histories, 2 communities of stars becoming one. Milkomeda will be larger than either galaxy alone, a new home for all those billions of suns. If you're still awake, that's wonderful. Just breathe. Our Milky Way and Andromeda are part of something called the Local Group, a cluster of about 54 galaxies, our cosmic neighborhood. Some are dwarf galaxies containing only a few billion stars. Others are irregular, shapeless clouds of light, but all of them are bound together by gravity, traveling through space as a family. 2 of our neighbors are called the Magellanic Clouds, the Large and Small Magellanic Clouds, visible from the southern hemisphere. To the naked eye, they look like fragments of the Milky Way, pieces that have drifted away into the southern sky, but they're separate galaxies, satellite galaxies, orbiting our own. The Large Magellanic Cloud is about 160,000 light-years away. Within it is the Tarantula Nebula, one of the most active star-forming regions in the cosmos. Right now, at this very moment, thousands of new stars are being born there, clouds of gas collapsing, heating up, igniting, brand new suns blazing to life The small Magellanic Cloud sits about 200,000 light-years from Earth. The light from that galaxy left those stars 200,000 years ago, long before humans built cities, long before we wrote languages, long before we looked through telescopes. That light has been traveling all this time just to reach your eyes tonight. Both Magellanic Clouds are slowly being consumed by the Milky Way. Over hundreds of millions of years, they're being pulled closer. Eventually, they'll be absorbed entirely. Their stars will mingle with ours. Nothing in the universe stays separate forever. Everything, eventually, comes together. There's another galaxy worth mentioning, the Triangulum Galaxy, also called M33. It's the third largest in our local group, a beautiful spiral about 2.7 million light-years away on exceptionally clear nights. Away from city lights, you can see it with binoculars, sometimes even with the naked eye, a faint ghostly spiral in the constellation Triangulum. Galaxies come in different shapes, and each shape tells a story. Spiral galaxies, like the Milky Way, have graceful curving arms. These arms are where new stars form, where the action happens, but the arms aren't solid structures. They're density waves, patterns that move through the galaxy, like ripples on water. Stars and gas clouds pass through these arms, and as they do, the increased density triggers the birth of new stars. Then there are elliptical galaxies. They look like glowing eggs or spheres. They're generally older, more settled. Most of their stars are ancient, red and yellow stars that have been burning for billions of years. Elliptical galaxies are quieter places. The frantic pace of star formation has slowed to almost nothing. They're retirement communities for stars, places where the drama has passed, leaving only the long, slow cooling of time. Some galaxies don't fit neatly into categories. They're called irregular galaxies. No particular shape, no spiral arms, no smooth elliptical form, just clouds of stars scattered in random patterns. Often, these shapes result from gravitational interactions, two galaxies passing too close, pulling on each other, warping each other's structure. They're cosmic sculptures, shaped by invisible forces. The largest galaxies in the universe are giant elliptical galaxies. Some contain over 100 trillion stars. IC 1101 is one of the largest ever discovered. It spans about 6 million light-years across. To put that in perspective, the distance between the Milky Way and Andromeda is only 2.5 million light-years. This single galaxy is wider than the space between us and our nearest large neighbor. If you're still listening, you're doing wonderfully. Just breathe slowly. At the center of most large galaxies, including our own, lies a supermassive black hole. In the Milky Way, this black hole is called Sagittarius A star, often written as Sagittarius A star. It sits right at the heart of our galaxy, in the direction of the constellation Sagittarius. Sagittarius A star has a mass equivalent to about 4 million suns, 4 million times the mass of our sun, compressed into a region smaller than the orbit of Mercury. Despite this immense mass, it sits quietly at our galaxy's heart, a silent anchor around which hundreds of billions of stars orbit. It doesn't rage. It doesn't consume everything in sight. It simply exists. Black holes are regions where gravity is so strong that not even light can escape. They're not holes in the conventional sense, not empty voids. They're regions of extreme density. All that mass compressed into an impossibly small space. the gravity warps the very fabric of space and time. Here's something that might surprise you. Black holes don't roam around, consuming everything in their path. They only affect objects that venture very close. If you replaced our sun with a black hole of the same mass, Earth's orbit wouldn't change at all. We'd continue circling at the same distance, the same speed, just as we always have. Of course, we'd be in darkness and cold, but the orbit itself would remain stable. Black holes come in different sizes. Stellar mass black holes form when massive stars explode. These typically have masses between 3 and a few dozen times that of the Sun. Then there are supermassive black holes, millions or billions of times the mass of the Sun, residing in galaxy centers. And there might be intermediate mass black holes too, though these are harder to find. In 2019, scientists captured the first ever image of a black hole. It was the supermassive black hole at the center of a galaxy called M87, about 55 million light years away. The image showed a dark circle surrounded by a glowing ring. That ring is matter, being heated to billions of degrees as it swirls around the black hole. A historic moment, seeing directly what had only been theoretical. Stars are born in nebulae, vast clouds of gas and dust, light years across, containing enough material to form thousands or millions of stars. They're among the most beautiful structures in the universe, glowing in vibrant reds, blues, purples, greens. This glow comes from gas, being energized by radiation from nearby hot stars. One of the most famous is the Orion Nebula, located about 1,344 light-years from Earth, close enough and bright enough that you can see it with the naked eye. Look for Orion's belt, 3 stars in a row. Then look at the sword hanging below. That fuzzy patch in the middle is the Orion Nebula. What appears as a small smudge is actually a vast cloud where stars are being born. Within the Orion Nebula, astronomers have discovered thousands of young stars. Some are only a few thousand years old, which in cosmic terms is like being born yesterday. These infant stars are still surrounded by disks of gas and dust, from which planets might eventually form. We're watching solar systems in the process of being born. The Eagle Nebula contains the famous pillars of creation, towering columns of gas and dust where stars are being born. These pillars are light years tall. Each pillar is taller than the distance from the Sun to the nearest star. Inside them, gravity is slowly pulling gas together, forming new stars, new worlds. If you haven't fallen asleep yet, that's perfectly fine. The light we see from the pillars of creation left them 7,000 years ago. We're looking at a scene from the distant past, preserved in light. Actually, scientists believe the pillars may have been destroyed by a nearby supernova about 6,000 years ago, but we won't see that destruction for another 1,000 years. The light from that event hasn't reached us yet. Nebulae glow because ultraviolet radiation from young hot stars causes the surrounding gas to fluoresce. It's nature's own luminescence, like a cosmic neon sign. Hydrogen glows red, oxygen glows green and blue, sulfur glows yellow, the colors of a nebula. Tell us what elements are present. The Carina Nebula in the southern sky is home to some of the most massive stars known. Eta Carinae, one of the most luminous stars in our galaxy, resides there. This star is so massive, so bright, that it's barely stable. It could explode as a supernova at any moment. Or it might have already exploded, and we just don't know yet, because the light takes time to reach us. Star formation happens when regions within a nebula become dense enough. Gravity causes them to collapse, slowly at first, then faster. Matter falls inward. The cloud spins faster, heats up, until finally, nuclear fusion ignites. A star is born. As the collapsing cloud spins, it flattens into a disk. At the center, temperatures rise. Millions of degrees, hot enough for hydrogen atoms to fuse into helium. This is what makes stars shine. Nuclear fusion, the same process that powers our sun. Around young stars, the remaining disk of material can form planets. This is how our solar system formed 4.6 billion years ago, and how countless other systems form today. Gas and dust, clumping together, growing larger, sweeping up more material, until planets emerge from the chaos. Stars spend most of their lives in a stable phase called the main sequence, fusing hydrogen into helium in their cores, shining steadily, peacefully. Our Sun is a middle-aged main sequence star. Halfway through its life, the Sun has been shining for about 4.6 billion years, and it has roughly another 5 billion years left before it exhausts its hydrogen fuel. Plenty of time for whatever comes next. Stars come in different colors, depending on their temperature. The hottest stars shine blue-white, surface temperatures over 30,000 degrees. Medium stars like our Sun glow yellow, about 5,800 degrees. Cooler stars glow red or orange, maybe 3,000 degrees. The color tells us how hot a star burns. Red dwarf stars are the smallest and coolest stars. They burn their fuel so slowly that some could shine for trillions of years, longer than the current age of the universe. They'll outlive every other type of star. When the last massive star has exploded, when the sun has cooled to a cinder, red dwarfs will still be burning. If you're still awake, just relax. Let your mind wander. The most massive stars live fast and die young. A star 100 times the mass of the sun might live only a few million years. They burn so hot, so bright, that they exhaust their fuel in a cosmic instant. When a star like our sun runs out of hydrogen, it expands into a red giant. In about 5 billion years, the sun will swell to engulf Mercury and Venus, possibly Earth too. But don't worry, that's so far in the future that it's beyond imagining. During the red giant phase, stars shed their outer layers into space, enriching the surrounding nebulae with heavier elements. This is where much of the carbon, nitrogen, and oxygen in the universe comes from. We are made from the remnants of dead stars. After expelling their outer layers, sun-like stars leave behind a hot, dense core, called a white dwarf. This remnant slowly cools over billions of years. Eventually, it will become a black dwarf, a cold, dark cinder, though the universe isn't old enough yet for any black dwarfs to exist. White dwarfs are incredibly dense. A teaspoon of white dwarf material would weigh about 5 tons on Earth, yet they're quite small, roughly the size of Earth. All that mass packed into a sphere the size of our planet. The most massive stars end their lives in spectacular supernova explosions. For a few weeks, a single exploding star can outshine an entire galaxy. Think about that. Billions of stars, hundreds of billions of suns, all shining together, and one supernova, briefly brighter than all of them combined. It's one of the most powerful events in the universe. A star saying goodbye. Supernovae are among the most energetic events in the cosmos. They release more energy in a few seconds than the Sun will produce in its entire 10 billion year lifetime. The explosion is so powerful, so brilliant, that it can be seen from billions of light years away. A flash of light traveling across the universe, carrying the news that a star has died. The Crab Nebula is the remains of a supernova observed by Chinese astronomers in 1054 AD. They saw what they called a guest star appear suddenly in the sky, so bright it was visible during the daytime for 23 days. At night, it was bright enough to read by. For nearly 2 years, it remained visible to the naked eye. Now, nearly 1,000 years later, we see the expanding cloud of debris, still glowing, still beautiful, the ghost of a star. Supernovae create and scatter heavy elements across the galaxy. The iron in your blood, the calcium in your bones, the gold in any jewelry, the oxygen you're breathing right now, all of it was forged inside stars and scattered through space when those stars exploded. We are made of stardust, not metaphorically, literally. Every atom in your body, except hydrogen, was created in a star. You are the universe experiencing itself. After a massive star explodes, what remains of its core can become one of two things. If the remaining core is less than about 3 times the Sun's mass, it becomes a neutron star. If it's more massive than that, the core collapses completely and becomes a black hole. Both are extreme, both are fascinating, both are peaceful in their own way. If you're still listening, and that's perfectly wonderful, just breathe slowly. Neutron stars are incredibly dense. They pack roughly 1.4 times the mass of the Sun into a sphere only about 12 miles across. Imagine the entire Sun, all that mass, compressed into something the size of a small city, Manhattan, but with the mass of the Sun. That's a neutron star. The density of a neutron star is almost beyond comprehension. A sugar cube-sized amount of neutron star material would weigh about 1 billion tons on Earth. A teaspoon would weigh as much as a mountain. Gravity there is so strong that if you dropped something from a height of 1 meter, it would hit the surface at millions of miles per hour. But don't worry, we're not going there. We're safe here, in our beds, drifting peacefully. Some neutron stars spin incredibly fast, hundreds of times per second. These are called pulsars because they emit beams of radiation from their magnetic poles that sweep across space like cosmic lighthouses. Each time the beam points toward Earth, we detect a pulse, regular, precise, like a cosmic metronome. Some pulsars spin so fast that they rotate more than 700 times per second. That's faster than a kitchen blender. The first pulsar was discovered in 1967 by a graduate student named Jocelyn Bell Burnell. She noticed a strange signal, pulsing with incredible regularity, every 1.337 seconds, never varying. The pulses were so precise that astronomers briefly wondered if they might be signals from an alien civilization. They even nicknamed it LGM-1, Little Green Men 1. But it turned out to be something even more remarkable. A rapidly spinning neutron star. Nature, not aliens. Though honestly, nature is more impressive. Pulsars are extraordinarily precise clocks. Some are stable enough to rival the best atomic clocks we've built on Earth. They spin at exactly the same rate, year after year, decade after decade. Scientists have even proposed using pulsars as a galactic positioning system, a GPS, for the entire galaxy, nature's perfect timekeepers, spinning in the darkness, keeping time for no one in particular. When two neutron stars collide, something extraordinary happens. They create gravitational waves, ripples in the fabric of space-time itself. These waves spread out across the universe at the speed of light. In 2017, scientists detected gravitational waves from two colliding neutron stars, and they also saw the explosion in optical telescopes and in X-rays and in radio waves. It was a historic moment, the birth of what they call multi-messenger astronomy, seeing the universe in an entirely new way. Stars often form in groups called star clusters. Open clusters might contain a few hundred to a few thousand stars. Loosely bound by gravity, they're like stellar families born together from the same cloud of gas. But eventually, they drift apart. Over tens or hundreds of millions of years, the cluster disperses. The stars go their separate ways. The Pleiades, also known as the Seven Sisters, is perhaps the most famous open cluster, visible to the naked eye, a tight group of bright blue stars in the constellation Taurus. To our ancestors, these clustered stars held deep significance. The ancient Greeks told stories about them. The Maori navigated by them. Indigenous Australians had their own tales. They're only about 100 million years old, young stars, still surrounded by wisps of glowing gas. If stars were people, the Pleiades would still be in their teenage years. Globular clusters are very different from open clusters. They're much denser, much older, containing hundreds of thousands, sometimes millions of stars, packed into a roughly spherical region. They orbit galaxies like satellites, slowly circling the galactic center, taking hundreds of millions of years for each orbit. Ancient, stable, beautiful, like cosmic cities floating through the darkness. Globular clusters contain some of the oldest stars in the galaxy, nearly as old as the universe itself, between 10 and 13 billion years old. Looking at a globular cluster is like looking at a stellar retirement community. Stars that have been shining since the early days of the universe. They've seen it all, the formation of galaxies, the birth and death of countless other stars. They're the elders of the cosmos. If you haven't drifted away yet, that's perfectly fine. Just let these words wash over you. Omega Centauri is one of the largest globular clusters visible from Earth. It contains about 10 million stars, all orbiting a common center of gravity, all held together by their mutual gravitational attraction. From Earth, it looks like a fuzzy patch, but through a telescope, it resolves into countless individual points of light. A city of ancient suns, all gathered together, all shining quietly. Measuring distances in space is one of the great challenges of astronomy. For nearby stars, within a few hundred light years, astronomers use a technique called parallax. It's based on the apparent shift in a star's position. As Earth orbits the Sun, it's like holding your thumb up at arm's length and closing one eye then the other. Your thumb appears to shift against the background. Stars do the same thing. As Earth moves through its orbit, the closer the star, the bigger the shift. The farther the star, the smaller the shift. For more distant objects, scientists use what they call standard candles. These are objects with known intrinsic brightness. By comparing how bright they appear to how bright they actually are, distances can be calculated. It's like seeing a light bulb in the distance. If you know it's a 100-watt bulb, you can estimate how far away it is by how dim it appears. The farther away, the dimmer it looks. Simple, elegant, effective. Type Ia supernovae are particularly useful standard candles. They occur when a white dwarf star accumulates too much mass and explodes, and they always explode with roughly the same peak brightness. This consistent brightness makes them visible across billions of light years. They're bright enough to be seen. In distant galaxies, astronomers use type Ia supernovae to make one of the most important discoveries in cosmology. They found that the universe's expansion is accelerating. Cepheid variable stars are another important tool for measuring cosmic distances. These stars pulse regularly, expanding and contracting, brightening and dimming, and there's a relationship between how fast they pulse and how intrinsically bright they are. This relationship was discovered by Henrietta Swan Leavitt in the early 1900s. Edwin Hubble used cepheids to prove that Andromeda was a separate galaxy, not just a nebula within the Milky Way. All these methods together form what astronomers call the cosmic distance ladder. Each method builds on the previous one. Each extends our reach a little farther into the universe, from parallax for nearby stars, to cepheids for nearby galaxies, to type Ia supernovae for the most distant reaches of space. Each rung on the ladder, each method, extends our vision, helps us map the vast cosmos. Just as stars cluster together, galaxies also form clusters. Our local group, with the Milky Way, Andromeda, and about 50 other galaxies, is actually a relatively small cluster, a modest neighborhood. Dozens of galaxies bound together by gravity, orbiting each other in a slow cosmic dance. The Virgo cluster is the nearest large galaxy cluster to us. It contains over 1,500 galaxies, about 65 million light-years away. Our larger neighborhood, a cosmic city. If the local group is a village, the Virgo cluster is a metropolis. From our perspective, the Virgo cluster occupies a region of sky about the size of your hand, held at arm's length. The Virgo cluster is gravitationally bound. All those 1,500 galaxies orbit around a common center of mass. Like bees around a hive, it's a slow dance, taking billions of years for each orbit. Everything moving, everything connected, everything held together by invisible gravity. Here's something fascinating. Our local group is actually being pulled toward the Virgo cluster. We're moving at about 1,000 kilometers per second, falling, slowly falling, into its gravitational embrace. In billions of years, we'll become part of it. The local group will merge with the Virgo cluster. More galaxies, more stars, all coming together. If you're still here with me, just rest. Let these cosmic stories carry you. Even larger than clusters are superclusters. These are groups of galaxy clusters, vast structures containing thousands of galaxies. We're part of the Virgo supercluster, which contains at least 100 galaxy groups and clusters. The Virgo supercluster contains around 47,000 galaxies, and it spans about 110 million light-years from end to end. Yet it's just one supercluster among millions in the observable universe. We're part of something incomprehensibly vast, and yet here we are on this small planet, in this quiet moment, safe, peaceful, about to sleep. Recent observations revealed that we're part of an even larger structure. It's called Laniakea, which means immeasurable heaven in Hawaiian. Laniakea contains about 100,000 galaxies. It spans 520 million light-years. Our cosmic address keeps getting longer. Earth, Solar System, Milky Way, Local Group, Virgo Supercluster, Laniakea. Between superclusters lie vast voids, regions with very few galaxies, almost empty space. These voids can span hundreds of millions of light-years, great empty expanses where almost nothing exists, just darkness and distance and the occasional lonely galaxy. The universe is mostly empty, but that emptiness has its own beauty, its own peace. The large-scale structure of the universe resembles a cosmic web, filaments of galaxies stretching between dense nodes, like a three-dimensional spider web made of light and gravity and matter. The nodes are where superclusters form. The filaments are where galaxies line up, and the voids are the empty spaces between. It's one of the most beautiful patterns in nature, structure emerging from chaos. This cosmic web formed over billions of years. After the Big Bang, matter was almost uniformly distributed. Almost. There were tiny variations, tiny differences in density, and gravity, patient gravity, amplified those differences, pulling matter together along certain paths, leaving other regions emptier and emptier. The universe, organizing itself, creating structure, creating beauty, from nothing but gravity and time. Einstein showed us something profound. Space and time are not separate things. They're interconnected, woven together into a four-dimensional fabric called space-time. And massive objects, like stars and planets and galaxies, curve this fabric. That curvature, that bending of space-time, is what we experience as gravity. Gravity isn't a force pulling on objects. It's objects following the curves in the fabric of reality itself. This leads to something remarkable called gravitational lensing. When light from a distant galaxy passes near a massive object, like a closer galaxy or galaxy cluster, the gravity bends the light's path. Sometimes this creates multiple images of the same distant galaxy. Sometimes it creates rings, Einstein rings, they're called. Space itself, acting like a lens, bending light, magnifying distant objects. Astronomers use gravitational lensing for many purposes, to study distant galaxies that would otherwise be too faint to see, to weigh galaxy clusters, to map the distribution of dark matter, because dark matter, which we cannot see directly, still has mass, and mass curves space-time, and that curvature bends light, invisible matter, revealing itself through its effects on light. Some of the most distant galaxies ever observed were only discovered because of gravitational lensing. A closer galaxy cluster acted like a cosmic magnifying glass, amplifying the light from galaxies billions of light years behind it. Nature helping us see farther, providing us with natural telescopes scattered across the universe. If you're still awake, and it's fine whether you are or not, here's something peaceful to consider. Gravitational waves are ripples in the fabric of space-time itself. When massive objects accelerate, especially when they orbit each other rapidly, they create waves like a stone dropped in a pond. But the pond is space-time itself. These waves spread out at the speed of light, carrying information about the events that created them. Gravitational waves were predicted by Einstein in 1916, part of his general theory of relativity, but they weren't directly detected until September 14th, 2015, nearly a century later. The detection came from two black holes, each about 30 times the mass of the Sun, colliding and merging 1.3 billion light-years away. The gravitational waves from that collision rippled across the universe, and finally, after traveling for 1.3 billion years, they reached Earth. The detectors that found gravitational waves are among the most sensitive instruments ever built. They're called LIGO, Laser Interferometer Gravitational Wave Observatory. They can detect changes in distance smaller than a proton, smaller than the nucleus of an atom. When a gravitational wave passes through Earth, it stretches space in one direction and compresses it in another by the tiniest amount imaginable. And yet, we can measure it. We can hear the universe singing. Now, let's talk about dark matter. It makes up about 85% of all the matter in the universe, but we cannot see it. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation at all. So how do we know it exists? Through gravity, through its effects on things we can see. It's invisible, but undeniably there. Galaxies rotate in ways that don't make sense based on the visible matter alone. The stars in the outer regions of galaxies are moving too fast. They should fly apart. The visible matter doesn't have enough gravity to hold them, but they don't fly apart. Something is holding them together. Something with mass, something with gravity. That something is dark matter, an invisible halo surrounding every galaxy, providing the extra mass, the extra gravity, keeping everything bound together. Without dark matter, galaxies would disintegrate, stars would scatter into the void, and then there's dark energy, even more mysterious than dark matter. Dark energy makes up about 68% of the total energy content of the universe. We don't know what it is. We only know what it does. It pushes. It causes the expansion of the universe to accelerate. Galaxies are not just moving apart. They're moving apart faster and faster. Some unknown force, some unknown energy is pushing the universe to expand ever more rapidly. We call it dark energy because we're in the dark about what it actually is. The universe is expanding. Every distant galaxy is moving away from us, and the farther away a galaxy is, the faster it appears to recede. This doesn't mean we're at the center. It means space itself is stretching everywhere, all at once. Every observer in every galaxy sees the same thing, all other galaxies moving away from them. This expansion doesn't mean galaxies are moving through space. It's more subtle than that. Space itself is stretching, growing, expanding. The galaxies are carried along like raisins in rising bread dough. As the dough expands, the raisins move apart, but the raisins themselves aren't moving through the dough. Galaxies aren't moving through space. Space is carrying them apart. This expansion was discovered by Edwin Hubble. In 1929, he measured the light from distant galaxies, and he found something remarkable. The light was shifted toward the red end of the spectrum. Redshifted. The farther away the galaxy, the more its light was redshifted. This redshift is caused by the expansion of space. As light travels through expanding space, its wavelength gets stretched, shifted toward the red, and the amount of redshift tells us how fast a galaxy is receding, how fast space is expanding. The fact that the universe is expanding means it was smaller in the past, much smaller. If you trace the expansion backward, running time in reverse, everything gets closer and closer together. Eventually, all the matter and energy in the universe was compressed into an incredibly small, incredibly hot, incredibly dense state. And then it began to expand rapidly, violently. This was the Big Bang, not an explosion in space, but an expansion of space itself. The moment when time began, when the universe was born. If you haven't fallen asleep by now, that's all right. Your mind is wandering. That's perfect. Just breathe. The cosmic microwave background radiation is the afterglow of the Big Bang, light that has been traveling through space for 13.8 billion years, since just 380,000 years after the Big Bang. Before that, the universe was so hot and dense that it was opaque. Light couldn't travel freely. It was scattered constantly. But then, the universe expanded enough, cooled enough, and light broke free. That ancient light is still traveling, still reaching us from every direction in space. This ancient light has been cooled by the expansion of the universe. When it was emitted, it was hot, thousands of degrees. But space has expanded so much that the light has been stretched, cooled. Now, it's just 2.7 degrees above absolute zero, the coldest possible temperature. It fills the entire universe, a faint glow in every direction, a whisper from the dawn of time. If you could see microwave radiation, the entire sky would glow softly, uniformly, with the memory of creation. When we look at distant galaxies, we're looking back in time. The light we see left those galaxies millions or billions of years ago. The farther we look, the further back we see. Telescopes are time machines, allowing us to witness the past. When we look at Andromeda, we see it as it was 2.5 million years ago, when early humans were just beginning to walk upright. When we look at the most distant galaxies, we see them as they were when the universe was young, just a few 100 million years old. The most distant galaxies we've observed formed when the universe was only a few 100 million years old. They're among the first galaxies to ever form. Cosmic pioneers, islands of stars, in an ocean of darkness. We're seeing them, not as they are now, but as they were then, near the beginning, in the cosmic dawn. Those galaxies, if they still exist, have evolved, changed, grown. But we won't see that for billions of years, because the light showing us what they look like now hasn't reached us yet. Despite all we've learned, despite all we've discovered, we've only begun to understand the universe. Each answer leads to new questions. Each discovery reveals new mysteries. What is dark matter? What is dark energy? How did the first stars form? Are we alone? Is there life elsewhere in the cosmos? So much is still unknown, so much still to discover. The universe keeps surprising us, keeps revealing new wonders, and that's beautiful. There will always be more to learn, more to explore. The cosmos is endlessly fascinating. And finally, this: the atoms in your body were forged in the hearts of stars. The iron in your blood was created in a supernova explosion. The calcium in your bones was made in a dying star. The oxygen you breathe, the carbon that forms your cells, all came from stars. Billions of years ago, those stars lived and died. They scattered their elements across space. Those atoms drifted through nebulae, gathered in clouds, formed new stars, new planets, and eventually, somehow, those atoms became you. You are made of stardust, literally, not poetically. Actually, You are connected to the cosmos in the most profound way imaginable. You are part of this universe, part of its long and beautiful story. From the Big Bang, 13.8 billion years ago, through the formation of galaxies, the birth of stars, the creation of elements, the formation of planets, the emergence of life, all leading to this moment, to you, lying here, tonight, about to sleep. So there you have them. 100 facts about our universe, about galaxies spinning through the darkness, about stars being born and dying, about the vast cosmic dance that unfolds across billions of light years and billions of years. As you lie here now, ready for sleep, remember that you're resting on a planet, orbiting a star in a galaxy among trillions, all moving through the expanding fabric of space. Yet here, in this moment, all is quiet, all is peaceful. The universe is vast, incomprehensibly vast, but you are here, safe, warm, ready for rest. Let these stories of distant galaxies and ancient light carry you gently into your dreams. Let the enormity of space remind you that your worries are small, your rest is deserved, and tomorrow will come softly, as it always does. The stars will still be shining when you wake. But for now, rest, breathe slowly, deeply, let go of everything. Let your mind drift through those spiral galaxies, through those nebulae where stars are born, through the cosmic web, stretching across infinity. You are stardust. You are part of the universe, and the universe wants you to sleep. So sleep now. Let these cosmic tales lull you into peaceful dreams. May you drift among the galaxies tonight. May you find rest in the infinite. Good night, sweet dreams among the stars.